Start with the essence question. So we've spent many days now talking about how to factor a trinomial. In essence, what is it that we're doing by factoring a polynomial? Who wants to say what it is, in essence? Someone say it? No?
It's like reverse distributing.
Well, that's a really nice way to say it. It's like reverse distributing, right? Because when you factor a trinomial like x squared plus 7x plus 12, and then you factor it into x plus 3, x plus 4, that is the reverse of FOIL, right? So if you had x plus 3, x plus 4, and you FOILed it, that would give you the trinomial. And so we're reverse FOILing. Yeah, that's absolutely true. That is true. What else can you say? In essence, what are we doing?
Making an addition problem into multiplication.
Exactly right. We're taking an addition problem, something plus something plus something, and we're rewriting it as a multiplication problem, something times something. That might not sound like gigantic, but today we'll see why that's such a gigantic idea. To be able to translate from addition to multiplication, like you translate from Egyptian into Farsi. Are those languages very different? I'm sure they are. So, yeah, this is a big deal to go from addition to multiplication. That's the essence of what we've been doing. Okay, so now my guessing game. I hope that you have lots of guesses. Who'd like to start out with the a plus b equals 10? Again, if you guess one of my numbers, I'll give you a penny. If you guess both of my numbers, I'll give you $100. So what numbers am I thinking of that add to 10? I'll just start calling on people. Erica? 5 and 5, great guess. No. Yes, you?
9 plus 1.
What is it?
9 plus
9 plus 1? No. But good guess. Yes, Pheasant?
6 plus 4.
6 and 4? No.
Simply negative plus positive.
Like what, Elda? Negative 9 plus what?
Plus 1.
Plus 1? I don't think that gives us 10.
Negative 1.
Oh, plus negative 1? That would give us negative 10.
Oh, shit.
How about negative 9 plus 19? Would that work? Negative 9 plus 19?
Yeah.
That would work out to be 10. Good guess, but no. John?
Negative 10.
Oh. 2 plus 8.
2 plus 8? No. Any other guesses on this one? Now, how many different guesses are there?
Infinite.
Yeah, there's infinitely many, right? No one mentioned decimals yet, but it could be 0.1 and 9.9. That would add up to 10. It could be negative 0.1 and 10.1.
What about exponents?
There could be exponents in there. Maybe it could be 2 cubed, which is 8, and then 2. So we could do something like that, sure. Yeah, so there's a lot of possibilities. Did you ever have a prayer of guessing my numbers? Never, right? If there's infinitely many possibilities and the real choice is only 1 out of infinity, 1 out of infinity is 0. You had 0 probability of ever getting $100 out of me on this game. Because guessing alone, you'd have never gotten there. By the way, my numbers were negative 2 and 12. Okay, so now how about my next game? How about a plus b equals 0? What numbers am I thinking of now?
Negative 10 plus 10.
Wait, Sarah, say it again.
Negative 10 plus 10.
It could be negative 10 plus 10. That wasn't it. What's another guess?
100
100 and?
plus negative 100.
Plus 100 plus negative 100? No, that wasn't it either. But it's a fine guess. Another guess, Nathan?
No idea.
We'll just guess any 2 numbers that add to 0.
Negative 99 and 1.
Yeah, negative 99 and, wait, and 1? That won't add up to 0.
Negative 99 and
Positive 99, very good. Okay, one more guess, Isis? Hey, 0 plus 0, that's a fun guess. All right, so none of those were my numbers either. But did you notice that at least with this game, the types of answers are a little more constrained? What can you say about the numbers now? Like previously when we were adding to 10, the numbers could have been anything and anything. But what do you notice about the numbers now?
100.
Yeah, they're the same number, but one is plus and one is minus. So it's interesting that as you change the game, it constrains the answers a little bit to what the numbers could be. But still, did you ever have a prayer of guessing my numbers? Never. No, you would have never guessed it. Mine was negative 0.1 and positive 0.1. Okay, so how about another game? A times B equals 10. So A times B equals 10. All right, what numbers was I thinking of?
The square root of 100 times 1.
Ooh, the square root of 100 times 1. Very good guess. That was not what I was thinking of, but that's a great guess. Jackie, what numbers was I thinking of? 2 times 5, great guess, but no. And April, what numbers were I thinking of? What is it? Oh, 10 times 1? No. But good guess. How about, let's see here, Sienna? What was I thinking of? Oh, 10 times 1 as well?
Yeah.
We'll try a different one. We've already covered 2 and 5 and 10 and 1, but we're not constrained to whole numbers. It could be anything. Brandon?
So 3 and then 3.3 with a 3 repeated.
Yeah, very good. So it could be 3 times 3, 3.3 repeating. Very good guess. That wasn't the one I was thinking of. It could even be something wild. It could be 1/3 times what? 30 thirds? Would that work? No, that wouldn't work. 1/3 times 30. There we go. 1/3 times 30. It could be a lot of different things. Okay, so none of those were it. Did you ever have a prayer of guessing my numbers? Right, just by guessing alone? You'd have never guessed it by guessing alone because there's infinitely many possibilities. Okay, so no. No one is ever going to guess that. Okay, so then the last game, A times B equals 0. So what were my numbers?
0.
Which one?
0.
0 times 0? Oh, dang it. That is not what I was thinking of, but you guessed one of my numbers. Who said that? Elda, I owe you a penny. You guessed one of my numbers. For sure, 0 was one of my numbers. Okay, but who can guess both of my numbers? What was it? Beth, what's your guess?
9
9 what?
times 0.
Ah, no, it's not 9, but you did guess the 0 part. I owe you a penny. What's another guess? How about Jessica? 8 times 0? No, it wasn't 8, but darn it, you did guess the 0 part. I owe you a penny.
0.1 times 0.
0.1 times 0? No, it's not 0.1, but you guessed the 0. I owe you a penny.
Can it be infinity times 0?
It could be, well, that's actually tricky. Infinity times 0 sometimes isn't 0, and sometimes it isn't infinity. Sometimes it could be anything in between. That's indeterminate. We call that indeterminate, and so that's not even going to be equal to 0. But that's a fine guess, indeterminate. Yeah, that really depends. Infinity is slippery. Okay, one more guess. How about Brandon?
1 trillion times 0.
1 trillion times 0. Very good guess. Not what I was thinking of, but you did guess one of my numbers, so I owe you a penny. Okay, so did you have a prayer of winning money off of me in this game?
Yeah.
Yeah, you were guaranteed to win money from me in this game. How much money were you guaranteed to win? A penny. That's it. That's all you were guaranteed. But it was guaranteed. I mean, if somebody had asked like 5 times 4, I would have been like, well, come on, that doesn't multiply to 0. So long as you were guessing 2 numbers that multiplied to equal 0, you were going to get one of my numbers, which was 0. My numbers were 0 and negative 13.
Wow.
Now, to be fair, I didn't actually have any numbers in mind.
Wow.
All right, that part really didn't matter. Yeah. Okay, so this is how the guessing game works. I want you all to consider historically. I want you to go back to the 1400s, maybe the 1500s. And at the time, their mathematics and technology was not nearly as advanced as ours. Now, I refer to mathematics as technology. Mathematics is a technology. So if you go back to the 1400s and 1500s, if a mathematician had this problem set before him, like x squared minus 17x plus 60, okay, equals 0. Right? At the time, this was actually a really hard problem. Like, this was hard. They didn't have the quadratic formula. They didn't have methods. So what would they do to try to solve this?
Find something that applies to 0.
Yeah, they would sit around and guess, right? That's what they were forced and kind of resorted to, was just sitting around and guessing. And back in the 1400, 1500s, mathematicians would duel with each other. Not with guns, but they would duel by sending each other problems and being like, here, solve this one. Right? And it was like throwing down. And then the other person was, you know, they had to respond within a day or so, or else they really lost face. It was embarrassing. So if I sent a problem like this to you, you would feel really pressured to find the answer. And if you didn't know how to find the answer, you were just kind of stuck, because how far is guessing going to get you? Everyone, let's go ahead and guess. What number do I have to plug in to make that plus that plus that equals 0? Go ahead and guess.
Negative 60.
Negative 60? If I plug in negative 60, so negative 60 squared, and then minus 17 times negative 60 plus 60, let's find out. Negative 60 squared is 3,600. And then this, oh, geez, I don't know what that is. That's like 1,000, positive 1,000, and wait, is it 1,420 maybe? No, that's totally wrong. I need a calculator. I'm not sure. I think it's 1,020. It doesn't even matter because is 3,600 plus 1,000 plus 60 going to equal 0? No.
What if you just plug in 0?
Okay, let's just plug in 0.
Oh, because you had the 60.
Yeah, if I just plug in 0, what will that be?
It's not
See?
That'll be 60 equals 0. So that didn't work. What's another guess?
So we had to make the x2 or the x to the second power.
Yeah, you need to
equal 0.
choose a number that when you square it and then multiply it times negative 17 and then add 60, it actually equals 0. Yeah, so what's another number? Let's guess. Any fine guess, Mohammed? 2. Let's plug in 2. Let's find out. Well, 2 squared is 4 minus 34 plus 60. We don't even really have to finish adding this because 4 minus 34 is negative 30. And negative 30 plus 60 didn't turn out to be 0. Okay, so that was not correct. Good guess, though, Mohammed. One more guess?
3.
3? All right, let's try 3. 3 squared is 9, so that's 9 minus 21 plus 60. Still not going to balance out to equal 0. One more guess? Does anyone feel lucky? Brandon? 10. All right, well, let's say 10. What if I plug in 10?
You can subtract.
So then 10, you can use a fraction, you can use a decimal, you can use anything you want. This one was 100 minus 170 plus 60. Ooh, who guessed 10? Brandon, you're really close. Look how close Brandon was. 100 minus 170 is negative 70 plus 60. He came out to be negative 10. That's like at least closer to 0.
It was negative 3.
Negative what?
Negative 3.
You want to try negative 3? If we try negative 3, then that would be 9 plus 51. What? Wait a minute. Oh, 9 plus 51 is 60. Too bad that wasn't a negative 60. That would have been really exciting. That would have balanced out to equal 0. Yeah. So, folks, do we have a prayer? I mean, do we have a prayer of guessing? I mean, maybe, maybe not. I mean, if you had a lot of time on your hands, you could sit here and you can just keep on plugging numbers in until finally one day you got the answer. Now, we could probably try to guess a little better, right? Because this is a positive number. And what's x squared? Anytime you square a number, it's positive. So this is going to be positive. This is going to be positive. So if I'm going to balance these out to equal 0, what had this one better be?
Negative.
Negative. So if this one had better be negative, what does that say about what x should be? X would have to be positive, right? Because a negative times a positive would be negative. So at least we narrowed down our guesses that x should be positive. But do we have any other guesses besides that? No, we're just guessing positive numbers. Okay, well, in all my guessing game, and then this game right here, my goal was to instill within you, a sense of dread, doom, and hopelessness. Did I? Are you filled with hopelessness and dread and doom? That it's pointless to try to guess the answer and how terrible that would be? All right, well, good. So along came then the 1400s, 1500s. Someone had a brilliant idea to solve problems like these. A brilliant idea, which we're about to say. Well, let's look at our calendar. Here we are. What is today? That's not our calendar. I'm sorry, folks. Today's September. This is not September at all. This is completely wrong. Let's just go back and I can look at my previous one. There we go. So today is February 15th. We have 2 more class periods, which should be enough to get work our way through chapter 6. And then we get to take our test the following Thursday. So a week from today. And that's it. So we'll go ahead and keep on working. I do have a joke for you today. Why is the math book always so unhappy? Why is the math book so unhappy? Because he has so many problems. Yeah, that's exactly right. You guys are nice. So many times I have students shout out from the back, like, because he sucks. I'm like, no, that's not the answer to the joke. All right, here we go. Okay, so reviewing what we've done, we've come a long way. We've learned all these different techniques for turning addition problems into multiplication problems, turning addition problems into multiplication problems. We have what I kind of grouped them together. Why did I group these two together? The GCF and the leading negative, what are you doing there? You're just kind of taking out one thing, right? You're either taking out a number or you're taking out a negative, but you're not really factoring it into binomials. You're just taking something out. What about this technique? Why did I group these together?
Factoring.
Yeah, it's pretty basic factoring where you either have a 1 on the x squared or you have a number on the x squared. Either way, you're going to end up with 2 binomials being multiplied by each other. And then why did I group these together? Difference of squares and perfect square binomial. Yeah, I mean, they're just kind of special cases. These are special cases. One of them, you're multiplying conjugates. The other one, you're multiplying the same thing times itself. So these are just special cases that we want to be familiar with. And then factoring by grouping is its own category because you have 4 terms instead of 3 or 2. So if you haven't done so already, I would make a little quick sheet like this, like on a note card, or tattoo it on your face, or something so that you're always remembering these skills right here. Because if I just give you some random problem and I say, turn this addition problem into a multiplication problem, these are the skills that you have. Okay, so everybody, let's turn to page 51. No, section 6.7, number 51.
Page 13.
Page 13. Thank you, Sina. All right. So here we are, folks. Let's cover the zero product rule. You can go ahead and write it in up at the very top. The zero product rule states, if A times B equals 0, then what do you know? If 2 numbers multiply to equal 0, then either, what's up, Eza?
Either A or B equals 0.
Yeah, either A equals 0 or B equals 0. It's got to be one of those. Either A equals 0 or B equals 0 or
Both.
or both equals 0. This is an absolute fact. This is what we got from our guessing game, is that if you're just guessing 2 numbers that add together to make something, you don't have a prayer. You'll never guess what 2 numbers add together to make something. And if you just say what 2 numbers multiply to make something, again, you don't have a prayer, unless the game is find 2 numbers that multiply to equal 0. Then you actually know something. You actually know something for sure. And that is that if 2 numbers multiply to equal 0, then one or both of them have to equal 0. And that's an insight. That's a very important insight that they had in, say, the 1400s, 1500s. Someone had this brilliant idea. They're like, hey, if 2 numbers multiply to equal 0, I actually know one of them is 0. And that was very helpful. So let's take a look at the first problem. In number 51, we know that x minus 6 times x plus 4 equals 0. That's the problem that we're given. Now, to just foil this together real quick, imagine that you were a mathematician in the 1400s and someone came up to you with the problem x squared minus 2x minus 24. All right, if someone actually presented you with the problem x squared minus 2x plus 24, you would again be instilled with that feeling of hopelessness, dreadness, and sadness. Like, oh no, how am I going to find the number to plug into this that actually makes this thing equal 0? Guessing will take too long. It could take forever to guess. So then someone had the brilliant idea. They said, well, what if we change this addition problem into a multiplication problem where the 2 things being multiplied equal 0? All right, then now we have a prayer. We can say, well, if this times this equals 0, what do I know about one of these?
0.
One of them is 0, right? And in fact, because I can let x be anything I want, I could say, hey, I can force this one to be 0 by choosing what value to make x to make that one equal 0. And in fact, I just go ahead and solve for it, and I say x is 6. If x is 6, then does this binomial equal 0?
Yeah.
6 minus 6 is 0? Yeah. So that's one possible solution. How about over here? If I force this binomial to equal 0, then all I have to do is solve for x, and I say x is negative 4. If I let x equal negative 4, will this binomial equal 0?
Yeah.
Yeah. One way or the other, this thing is going to equal 0 if I just let x equal 6 or if I let x equal negative 4. So everybody, copy down what I have here. Draw the arrows. Very important. Draw the arrows. You're going to say, okay, if this binomial times this binomial equals 0, then either this one can equal 0, and then you solve for x, or this one could equal 0, and you solve for x. These are your 2 solutions of a quadratic equation. Again, the quadratic equation, the original quadratic equation was x squared minus 2x minus 24. But then you factored it using this clever insight of turning addition into multiplication. And from there, you were able to say, well, something times something equals 0 means either this one could be 0 or that one could be 0. Now, let's just verify what we did here. What if I plug 6 into this expression? What if I plug 6 into this expression? I'm going to say let x equal 6. Then what would we have? We'd have 6 minus 6 is 0, times 6 plus 4 is 10. And is that a true statement? Is 0 times 10 equals 0? It's true. So that's good. That's true. X equals 6 really was a solution. Now, what if I let x equal -4? If I plug -4 into this expression, what do I get? I would get -4 minus 6 is -10. And then -4 plus 4 is 0. And is that true? Is -10 times 0 equal to 0? Yeah. So we just did it. We just found the only two numbers in the universe that I can actually plug into this statement that will make it equal 0. And more importantly, we just found the two numbers in the universe that you can plug in to that equation to make it equal 0. So let's just check. If I plug in 6 into this, will it work? Will it equal 0? I mean, it better. 6 squared is 36. Minus 2 times 6 is 12. Minus 24. And what's 36 minus 12 minus 24? 0. So that worked. Now how about -4? If I plug -4, -4 squared is 16. And then -2 times -4 is plus 8. And then minus the 24. Well, again, 16 plus 8 is 24. And 24 minus 24 is 0. So this right here, these two little arrows that I just drew, to consider the two possibilities when those binomials would equal 0, was the insight that was necessary in the late 1400s to allow mathematicians to break wide open polynomial problems that previously were fairly unsolvable. So let's try that again. Number 52. You're given a problem, x minus 0.6 times x plus 0.7. And let's just all agree on the type of work we're going to show for full credit. When you're given a problem and you have something times something equals 0, you're going to draw two arrows. You're going to say, well, either this binomial could equal 0, or this binomial could equal 0. Either way, my original expression would indeed multiply to equal 0. So then you solve both of them. So my first one, my solution would be x equals 0.6. And my second one, my solution would be x equals -0.7. And that's it. Those are the two solutions for that problem.
Do you want us to plug it into check?
Well, I think that you could do that visually, for instance. Like, so thank you, Elda, for the question. I would check. So what if you plug 0.6 in right here? 0.6 minus 0.6? That's 0. What if you plug in -0.7 here? -0.7 plus 0.7? That's 0 too. So you can probably check this visually just by confirming. But if the problems are a little harder, you might need to actually plug it in to check. But that's it. That's how the zero product rule works. Let's try two more down there. This next one has fractions in it. Do you imagine it works the same way even though there's fractions? So 53 is x plus a fourth and x minus 3/5. Notice the key thing here is not that it's a fourth or 3/5 or what the numbers are. The key thing is that fundamentally we have a multiplication problem. The fact that this binomial times this binomial equals 0, that allows us to use the zero product rule, that if two numbers multiply to equal 0, one of them has to equal 0. And in fact, I can make this one equal 0 by just choosing x to equal -1/4. If I plug -1/4 into this equation, that first binomial will equal 0. Or if I take this binomial and set it equal to 0, then x equals 3/5. If I plug 3/5 into the original equation, then that binomial will equal 0. And those are your two solutions.
Can you just flip the signs?
Well, now that's a great question. Does this mean that whenever you see two binomials, you can just change the signs and say, oh, look at that. The answer is going to be -1/4 and +3/5?
For 54, there's 3y. It's just
Yeah, so definitely not here because you have to solve for y, which means you'll move the 11 over and you'll divide by the 3. But in this case, sure, it is just changing the sign. But why does it change the sign? Because what are you really doing to the 1/4? You're moving it over to the other side of the equation, right? And that's what changes the sign. So yes, Elda, as a shortcut in your head, you can think to yourself, well, I'm just going to move that to the other side of the equation, which is what changes the sign. So long as you're memorizing it that way, well, I'm going to move that to the other side of the equation, so that changes the sign. Rather than just telling yourself the shortcut, just change the sign. Yeah. Okay. Well, let's try that last one, folks. Number 54. You're presented with the problem 3y plus 11 times 7y plus 5. And you know that that's equal to 0. then you use the zero product rule. You say, well, this binomial times that binomial equals 0. So either this binomial can equal 0 or this binomial can equal 0. Either way will achieve the result of something times something equals 0. So to Elda's question, right now you're going to move that 11 over to the right. So that's 3y equals negative 11. And then you divide off the 3, so y equals negative 11 thirds. And that's one solution. And in the second problem, you move the 5 over, so that becomes negative 5. And then you divide off the 7, and you get y equals negative 5 sevenths. And look at these solutions. You know, negative a fourth, negative 11 thirds. Would you have ever guessed those? No one would have ever guessed those. Not really. So the guesswork only gets you so far. Whereas this keen insight to take a polynomial and change it from an addition problem into a multiplication problem, that was the keen insight that was necessary in order to solve a whole new host of problems that previously people didn't know how to solve. Can you imagine what it must have been like for that person waking up that cold day in the 1400s? They just woke up one day and they're like, well, I'm going to work, to my mathematical work. What should I do today? Try making it equal 0? Like that was part of the thought process, right? Like, what should I do today? Oh, I don't know. Turn an addition problem into a multiplication problem? Like, I don't know what thought process happened with them, but somehow they must have had that insight. And now we all get to benefit. Okay, so moving on, let's try 55. This is a genuine polynomial problem. And again, you might guess this one. Folks, you might guess it. What number squared minus itself would equal 20? Try guessing. Because I bet you guys can guess this one. What number squared minus itself equals 20?
5.
Does 5 work? 5 squared is 25 minus 5? That's 20. Now, Kylie, how did you get 5?
Just guessing.
Just pure guessing. Did you walk your way through 1, 2, 3, 4, 5? Or you just...
No, it kind of just came to me that 5 squared equals 25.
Ah, okay, so it kind of got you in the ballpark of 20. Okay, yeah, that works. Alternately, you could be a systematic guesser. You could say, well, 1 squared minus 1 is 0, 2 squared minus 2 is 2, 3 squared minus 3 is 6, and you could just work your way through all the possibilities until you get there. Well, let's go ahead and do it the real way, folks. Everybody, we're going to do our first genuine polynomial problem where we use the zero product rule to solve it. You'll notice that for the last 4 class periods, we've just been factoring. We haven't solved any equations. Have we? Have we solved a single equation? No. Whereas now we're actually solving an equation. We've got our equal sign there, and we want to find what number can I plug in to make this equation true. Now remember, what does it mean to solve an equation? What are the 2 things it means? I asked this question on the test. If I say from here x equals 5, that means 5 is the x-intercept, and 5 makes the equation true. Right? Those are the 2 things we mean when we say x equals 5. It makes the equation true, and it's the x-intercept on the graph. Okay, so let's do it. Let's solve this equation. What do we need to do first? In order to use the zero product rule, what do we need? Say it again, Sino? Yeah, you need to bring the 20 over here to the left, because why?
It needs to equal 0.
Yeah, we need our equation to equal 0. That's key. In order to use this insight, that something times something equals 0, of course we need the whole equation to equal 0. And this is so fundamental, we call this standard form. Why do we call this standard form? That something, something, something equals 0? Because this is the form that allows you to use the zero product rule. So this is the standard way of presenting equations in mathematics now. Because at any given moment, you might turn an addition problem into a multiplication problem and use the zero product rule to get your answer. Okay, so now what? We just factor? What numbers multiply to make 20? Then add to make 1?
Negative 4 and 5.
Is it negative 4 and 5? Let's just double check.
Negative 5 and 4, sorry.
Is 1 and 20, 2 and 10, 4 and 5. I need a difference of 1, so that would be 4 and 5. I need a negative 1, so that'd be a negative 5 and a positive 4. So everyone, we would just write down our answer, x plus 4, x minus 5. And the only key difference now with what we were doing and what we're doing now is that you have to keep writing equals 0. This is an equation now. It's not just a disembodied expression that we're factoring for fun. Okay, so now something times something equals 0. So you draw your arrows. You say, well, either I can make this thing equal 0 by making x plus 4 equal to 0, or I can make x minus 5 equal to 0. And then since there's no number on the x to this point, you can just change the sign, which you're really just moving the number over to the other side. And our solutions are 5 and negative 4. This is really fun and helpful because you'll notice Kylie and probably many of you guessed 5. Would you have immediately guessed negative 4? No. Would you even have known to keep guessing? Like, gee, maybe there's another solution besides 5. Probably not. But this solution strategy tells you that there were actually 2 solutions, even when one of them was obvious and one of them was not very obvious. Now, folks, do both of these work?
Yeah.
We already checked the 5. If you plug in 5, it works. Does negative 4 work? What's negative 4 squared? 16. What's minus negative 4? That's a plus 4. So 16 plus 4 is 20. So it really works. Those are our 2 solutions. So negative 4 and 5 are the solutions to this quadratic because they make the equation true, and because on your graph, they would be the x-intercepts of the graph. Let's try another one. There we go. We got a whole bunch of them to try. What's our factoring strategy here?
Adds up to the middle number, multiplies.
Yeah, this is basic factoring. What multiplies to make 22, that adds to make 9. What's our factoring strategy here?
Gonna take the 5 out.
Yeah, we're going to take the 5 out, and then we can do basic factoring. What's our factoring strategy down here? Yeah, we can't take the 6 out, so what will we have to do?
Multiply 6.
Yeah, we'll have to do the non-basic factoring of 6 times 10. Okay, well, let's do it, folks. We have 3 fun factoring problems to do, which we actually get to set as an equation and use the zero product rule to actually solve. So I'm going to do one more with you right now. So x squared plus 9x minus 22. What numbers multiply to make 22 that add to make 9?
11.
Yeah, 11 and 2. And since it's negative 22, we need the difference. So let's see, that's 2 and 11. And we need it to add to a positive 9. So that's positive 11 and negative 2. So that'd be x minus 2 and x plus 11. And remember, folks, let's be professional about this. You have to keep writing equals 0. It's so easy to forget that, to just kind of forget about the equals 0 and just keep writing and find our solutions. But it's technically an equation, and we want it to be technically true. So we write equals 0, and we then drop down our arrows and say, well, either x minus 2 equals 0 or x plus 11 equals 0. Either way, I can get this product to equal 0. And so x equals 2 and x equals negative 11. Those are the only 2 values in the universe that you can plug into the original equation to make it true. And I encourage you to check it. You know, whenever you get a solution, actually go back and check. You can do it mentally or on your calculator. You can say, well, 2 squared is 4, and 9 times 2 is 18. And 4 plus 18 is 22, minus 22 is 0. So yes, this one works. Smiley face. And then you check the next one. You say, well, does negative 11 work? Negative 11 squared is 121. And then 9 times negative 11 is minus 99. And 121 minus 99 is 22. And 22 minus 22 is 0. So it worked. And so I get another smiley face. All right, folks, go ahead and try out number 57 and 58. This is a nice review of factoring strategies. So in number 57, factor out the 5 first, and then factor. And then in number 58, multiply the first term times the last, and you're going to rewrite the middle term and factor by grouping.
How do you know when to multiply the last term? Or something else?
Well, like here, you can take out a 5, and that will make the x squared have a 1 on it. Whereas here, you can't factor out anything, so you're stuck with the number on the first term. So that's one. Anytime you're stuck with a number on the first term, you'll have to multiply the first term.
Yeah, sure. Yeah.
So you just ignore it?
You should go past x. Just take that x out. There's no x on the last term. You can just take out 5.
Yeah.
And that'll leave you with x squared minus 7.
Because the answer on the right is 1.
And now we have some big numbers. I'll take that one. I see.
Multiply that 6 by 10, we just leave the rest of the rest.
Yeah, you know what? I'm going to talk about that specifically, but you would keep the 5 out front, and then just this one and this one actually into a solution. The 5 doesn't take this
Oh, never
data.
mind.
You would just have x. Oh, so this is this going to be. Yeah. Return to view.
I'm not sure it's. Because like 57, you have to find. So 5 goes into the lower numbers. So 1, 7, 12. Like if you do the regular 5 and divided by 5, 1, so you divide it by 7. From here, like the oh, and then the equal to 0. But then so what you just have one, right?
Oh.
All right, let's review the next two. In the number 57, we just had to take out the 5 first. And then let's talk about what happens to the 5. What is the fate of 5? So first, let's take out the 5. Sienna, when I factor out my 5, what do I have left? Yeah, plus 12. Okay, very good. Now, folks, let's just look at this right now. What's that 5 doing? I mean, it's just there, right? It's just sitting there being multiplied by that. Well, let's keep thinking about the 5. What happens now after I factor the x squared minus 7x plus 12? What were the two numbers that multiplied to make 12 that had to make negative 7? Negative 4 and negative 3?
Yeah.
All right. So x minus 4, x minus 3. And all that equals 0. Now, is this a multiplication problem? It is now. So I have this binomial times this binomial times 5. And as a matter of fact, what I have is a triple multiplication problem. I'm saying this times this equals 0. And the zero product rule works if you have 2 terms or 3 terms or 5 terms. If you have a whole bunch of things being multiplied to equal 0, any one of them has to equal 0. So can I make x minus 3 to equal 0? Sure, if I just let x equal 3. Can I make x minus 4 to equal 0? Sure, if I just make x equal 4. Can I make 5 equal 0?
No.
No, that's just silly, right? The 5 can't equal 0. So the 5 is essentially not an important part of this problem anymore. We factored it out. And it's so unimportant, in fact, that we could get rid of it. How could we get rid of the 5? I think I might have heard it.
Divide.
Yeah, we could just divide the 5 off to the other side, right? And what happens when we divide the 5 off to the other side? 0 divided by 5 is still 0. So, in fact, the 5 completely becomes immaterial to the problem. Because all we're really wondering about is the product of the x minus 4 times the x minus 3. So when we factor out a number from a problem like this, what happens to that number? It's gone. It goes away. It's no longer part of the product that's important to us. Okay, so then by the 0 product rule, what is x equal to? 4 or 3. So those are the 2 numbers that you can plug into that equation that will make it true. All right, very nice. How about this next one? This will be a nice practice to review how to solve a problem where the x squared term has a number on it. First of all, can we factor out any numbers from here? No. No, we can't factor anything out. So we're stuck with the 6. So how do we factor when there's a number on the first term? Yeah, multiply the first times the last. So 6 times 10 is 60. One of our favorite numbers because it's so highly factorable. So 1 and 60, 2 and 30. Now, before I make my whole factor table, what are we looking for? Something that adds to 19, right? So far I've got 61, 32. I'm going to keep going until I find something that adds to 19. So, what's that?
3 to 20.
3 and 20? Well, that won't add to 19. Or are you just telling me the next one?
4 and 5.
4 to 15.
Oh, okay. Let's see. 4 and 15. Yeah, there we go. 4 and 15. Yeah, so we are done with the factor table because we found 2 numbers that multiply to make 60 that add to make 19. Okay, so now what do I do with my 4 and 15?
You rewrite the problem.
You rewrite the middle term. So let's rewrite the middle term. We have 6y squared. Now, does it matter if we put 4y plus 15y or 15y plus 4y?
It doesn't matter.
It doesn't matter, but do we have a preference?
Yeah.
If you did the
4
15, you
first
could
and
divide
then
it by 3.
Yeah, I mean, if you do the 15 first, you can take out a 3. But if you do the 4 first, you can take out a 2. It completely doesn't matter. It's whatever you're in the mood for. You know, if you're in the mood to divide out 3s, do the 15. If you're in the mood to divide out 4s, do the 4. I'll just do the 4 because why not? So 14y plus 5y plus 10. 15y, that is. Okay, and then we factor by grouping. You check to make sure there's a plus sign in between them because right now this is still an addition problem. All right, so then what can we factor out of 6y squared plus 4y?
2y.
Yeah, 2y. So then we have 3y plus 2. And what can we take out of 15y plus 10?
5.
Just a 5. So that gives us 3y plus 2. And very lucky for us, it's 3y plus 2, 3y plus 2. That means that we're doing it right, and we can continue to factor the problem. So we end up with 3y plus 2 times 2y plus 5. So remember, for the last 4 class periods, that was our goal in and of itself. We would have stopped right there and said, whew, converted that addition problem into a multiplication problem, and we would go home for the day. But now we're actually solving an equation, and we're using this 0 product rule to say, well, if something times something equals 0, then either one of these can be 0, and in fact, I can make both of them equal 0. If I just choose my y value carefully enough, I can make this thing equal 0, and I can make that thing equal 0. So we say 3y plus 2 could equal 0 if 3y equals negative 2, y equals negative 2/3. So that's one possibility. I can make this binomial equal 0 by letting y equal negative 2/3. Or I can make this binomial equal 0 by choosing to make 2y plus 5 equal 0. And so 2y equals negative 5. And so y equals negative 5/2. And there's my other solution. Would you say that's a long math problem? I mean, maybe yes, maybe no, maybe depending on your context. It's a decent sized math problem, that's for sure. It's not nothing. You know, how many lines do we have? Start with the problem statement and then 1, 2, 3, kind of 4 lines of work at least, let alone the factor table to choose your number. So it's definitely a decent, meaty math problem. It's not trivial, but it's not the worst thing you'll ever do. Okay, any thoughts or feelings about the 0 product rule? I know I might sound super geeky when I say this, but the zero product rule was such an important advancement in technology in the 1400s. This was such a great new idea that they had to just convert addition problems into multiplication problems, because then they could solve problems deductively, analytically, and logically, rather than just by guessing, right? That's a huge advancement for humanity, to shift from guessing to logical deduction. Okay, there's a couple special problems up here. Oh yeah, good. Okay, so there's a couple special cases. Let's all take a look at 22n squared plus 6n equals 0 together. What's weird about this problem? Or is nothing weird about this problem? What's different about this problem?
There's only 2 to 10.
Yeah, so there's only 2 terms. So, not quite sure how we would go about doing our trinomial basic factoring technique, because there's not even a number at the end to say, what do you multiply to get something to add to make 6? And plus, we have a number on the n squared, so we wouldn't be able to do basic factoring anyway. So what do we do? What's always the first impulse we should have? Yeah, take out anything we can. So can we take anything out of this expression?
2.
Yeah, we can take out a 2. Anything else? Did we say n?
Yeah.
Yeah, we can take out a 2n. Let's do it. If I take out a 2n, what are we left with? 11n plus 3? Yeah. So, look, we already have a multiplication problem. We've already done it. This is a multiplication problem. I've got this thing times this thing equals 0. So it could be the case that you don't even have to do anything massive, in terms of doing this very, very long factoring process. As soon as you can take out a GCF, a greatest common factor, you might already have a multiplication problem that would allow you to set each of them equal to 0. Even though this one's a monomial and that one's a binomial, doesn't matter. We have an n in each of these. And what you'll notice most is that each of those equations is simple. 2n equals 0, easy. 11n plus 3, easy. This is the other part of this technological advancement that's cool. We start with one problem that's hard, right? 22n squared plus 6n. That's hard. What makes this problem hard? The n squared. So by converting an addition problem that's hard into a multiplication problem, what do we end up with? 2 problems that are easy. All right, that's another part of the conceptual philosophical thing that's happening here. We start with one hard problem and we turn it into 2 easy problems. That is also what made this technique so great. Okay, so finish solving, folks. One value is n equals 0. And the other value is 11n equals, no, n equals negative 3/11. Well, all right. Those are the 2 values that you can plug in for n that will actually make that equation true. And if you were to graph that equation on a graph, the x-intercepts would occur at 0 and negative 3/11. So far, bless you. So far, all the equations we've looked at have been already equal to 0. Take a look at number 60. Is that equal to 0? It is not. So what's going on with 60? Is it already a multiplication problem?
Yes.
It is already a multiplication problem. Can I just go ahead and say, hey, that times that equals 42, so either this is equal to 42 or this is equal to 42? Is that how this works? That is not how this works. It might be tempting. But the only way the zero product rule works is because it's a 0, not because it's a product, right? So that would give us the wrong answer anyway. I mean, obviously x is not 42, because then 42 times 41 would not be 42. So that's not the right approach. It has to be equal to 0. So what do we have to do? Yeah, we need to distribute and bring everything to the left. That's our goal. Always distribute, FOIL, whatever you need to do, bring everything to the left, and look at a genuine trinomial. Right? You need to be looking at a genuine trinomial. So let's do it. We distribute. We have x squared minus 1x equals 42. And then bring the 42 over to the left. So we really have x squared minus 1x minus 42 equals 0. Again, folks, maybe write this down. This is standard form. What makes it so standard?
Because we can do it too. We could use that to make it equal to 0.
Yeah, first, primarily because it's equal to 0. That's what makes it standard form, is the fact that it's equal to 0. Because now all we need to do is change this addition problem into a multiplication problem, and then we can use the zero product rule to actually solve our problem. Okay, we'll go for it, folks. 1 multiplies to make 42, that adds to make -1.
6 and 7.
Is it 6 and 7? You know, after a while, you get the hang of this, and then you might just say to yourself, well, I know it's 6 and 7, so you write it down, and then you figure out the signs. All right, so what signs would I need?
Positive, negative.
Yeah, +6 and a -7. Now, I'm not necessarily suggesting this. I'm just saying that as you go about your normal life, if you're just walking down the street and you're factoring things in your head, you can do this. On the test, you'd still want to show me your work. So you would say, -42, I know that's going to be 6 and 7. It has a difference of 1. And I'm going to make the 7 negative and the 6 positive. So I'd still want to see that on your test. But here we go. We're ready. We split that up. And so x plus 6 could equal 0. X minus 7 could equal 0. And so x equals -6 or x equals 7. Before we move on, let's look at this problem again. What is this problem asking you to find? 2 numbers that multiply to equal 42. Well, do you know of any numbers that multiply to equal 42? You all know lots of numbers that multiply to equal 42, right? We've got 1 and 42 and 2 and 21 and 3 and 14 and 4, no, 4, 5, 6, and 7. Those are all the numbers that multiply to equal 42. So I need something times something to equal 42. It could be any of those, or it could be a decimal. I don't know. But do you see any numbers in here that multiply to equal 42 that have this relationship? What is this relationship? On a number line, let's say the number x is right here. Where would the number x minus 1 be?
On the left.
Just to the left of it. Right? We're looking at 2 numbers on a number line that are right next to each other. Like this could be the number 5 and 4. It could be the number 10 and 9. Do you see any numbers on the factor table that are 1 unit apart? 6 and 7. So in fact, we could have already gone ahead and just solved this problem using our knowledge of factor tables. Just by knowing a factor table, you can say, well, what multiplies to equal 42, where the 2 numbers are just 1 unit apart. So we would go ahead and say that x is 7, and x minus 1 must be 6, and that's my solution. So x equals 7, and then 7 minus 1 is 6. And so 7 times 6 is 42. Looking at it that way, does that tell us the other solution? Because there were, in fact, 2 solutions. Does that tell us the other solution? Probably not. Not as quickly or as insightfully. But notice, the other problem was -6. What's the number just to the left of -6 on a number line?
-7.
-7. And is that still going to give us the right answer? If this is -6 times -7, does that still give us 42? Yeah. So this is interesting. I just want to throw this out to you that we do actually, other than the gigantic machinery of factoring and zero product rule of the skills that we're building for this class, there's also a shortcut strategy that from time to time I'm going to suggest, hey, you might want to consider just thinking about factoring numbers and if that would help you solve the problem. All right. Well, folks, that's the zero product rule. That's how we use the zero product rule to take everything we've been doing and give it purpose. So we have 4 word problems I'd like to get through today. These 2 and these next 2. And I'm hopeful. And that'll be our day. So let's start out by looking at number 61. Everybody, what I'd like you to do is just read it to yourself and just think about what's happening in this problem. Go ahead, read the problem statement. What is this problem about?
Area.
Oh, very nice. It's about area. That's true. What object is this problem about? A rectangle. So essentially that's what we're talking about in this problem. We have a rectangle, it has a particular length, it has a particular width, it has a particular area, and what do they want us to find? The length and the width. So let's just think about, we're at the end of the problem, what should my answer look like? It says find the length of the width of the rectangle, so my answer should be a length and a width, right? So when all is said and done, my answer should be something like this rectangle had a length and a width of 5 and 10. Right? That would be the answer to the problem. Should the answer to my problem be x equals 7? Is that a length and a width? No. So let's just keep in mind that when we read word problems, we're not just single-mindedly focused on solving for x. We're focused on answering the question at hand, which is, what is the length and the width of this particular rectangle whose sides have this relationship and it has the area of 60? So let's just keep that in mind. Okay, before we begin, I want to share with you that every word problem that we ever do in this class is going to have 4 steps and 4 elements that I will look for on your tests to give you full credit. So the first step is drawing a good picture. Right, just about any math problem, a picture is going to help you solve it. So let's start by drawing a good picture. Here they say a rectangle. Stop right there. How is this? Is that not the best rectangle you've ever seen in your life? Now, folks, should I have drawn this?
That's square.
That looks a little bit too much like a square. Make sure that your rectangle that you draw right now looks like a rectangle and not a square. Okay, we're not trying to be artists, but we do want our drawings to be suggestive of the reality of the problem. So make sure your rectangle is longer in one direction than in the other, okay? So a rectangle has a length of x plus 2 and a width of x minus 2. Which should go where? Should this be x plus 2 and that x minus 2? Or should that be x plus 2 and that should be x minus 2?
The length is the bigger section.
Yeah, the length is the bigger one. So which expression should go here?
The plus 2.
The x plus 2, not the minus 2. So that's a couple considerations so far. We want our picture to be a good picture, a really good picture. If it's a rectangle, make it look like a rectangle. If one of these sides is obviously bigger than the other, put that one on the longer side. I can't tell you how many times I've seen like a problem say, draw a rectangle, and then someone draws a square. Or it says, draw a rectangle with sides 10 and 4, and people label this. Don't do that. That doesn't look like 10 and 4. That's the 4. That's the 10, right? So let's be very conscious about the choices that we're making when we draw a picture. All right, so how are we doing so far? A rectangle has a length of x plus 2 and a width of x minus 2, and it has an area of 60. So I'm just going to go ahead and write down inside area equals 60. Why did I write area equals 60 inside as opposed to outside? Because it's the area of the rectangle inside. So that's helpful to your brain and your audience that we're labeling things appropriately. Okay, is that the end of the problem? It says find the length and the width of the rectangle. That's the end of the problem. So what do we do now? That was step 1, draw a good picture. And a good picture captures all the details of the problem statement. Step 2 is build an equation. Build an equation. Did they give us the equation to solve?
Yes.
Oh, they did? I mean, they literally gave you the equation? Something, something, something equals 0? No, they didn't give us the equation. We have to build our own equation. No one's ever going to just walk up to you and give you the equation. You'll have to build that yourself. So what concept are we using in this problem? Area. And what's the formula for area? Length times width. So let's go ahead and write down the formula. Area equals length times width. And how do we plug all of our information in now?
60
Yeah, 60.
equals x plus 2.
Yeah, equals the x plus 2 and the x minus 2. Now even here, make sure that you're putting the x plus 2 under L. It's not just arbitrary. Don't just write down x minus 2, x plus 2. Is that true to the problem?
No.
Was the length x minus 2? No, the length was x plus 2. We really want to make very conscious decisions about everything that we do. Okay, now that's our equation. I would make a recommendation. Where do we want everything to end up?
On the left side.
Over on the left, right? So actually, anytime I do an area equals length times width problem, I actually write it down backwards. Length times width equals area. Because that way, I've got my x plus 2 and my x minus 2, and my 60 over there. And when I go to move everything to the left, all I have to do is move the 60. That's just a little more convenient for me. Okay, so we did it. We built an equation. So far, we drew a really nice picture, check. We built our own equation, check. And so step 3 is the actual algebra. This is where we actually solve for x. So now we're ready to start doing the machinery, the actual algebra. So what do we need to do to make this thing equal 0?
Subtract the 60.
We need to bring the 60 over, and
Should we FOIL first? Though?
and we need to FOIL, because we need to turn this thing into an addition problem first. We need to get this thing just a standard polynomial to begin with. So let's go ahead and FOIL. So first, x squared, outer, minus 2x, inner, plus 2x, last, minus 4. That all equals 60. And what happens when you multiply conjugates?
The two middle terms cancel out.
Yeah, your middle terms cancel out. So we have x squared minus 4 equals 60. Okay, well, that was just the foiling part. We still need to bring everything over to the left. So let's go ahead and minus our 60, minus our 60. And now we have x squared minus 64 equals 0. Everything we just did right there was just to put our equation in what form?
Standard.
Standard form. So we now have it in standard form. Okay, well, now we need to factor it. Do you recognize what strategy we're going to use to factor x squared minus 64? This is difference of squares. 64 is the square number 8 squared. X squared is x squared. So we can really say now this is x squared minus 8 squared. And so our factoring is x minus 8, x plus 8. Is that correct? Is that the difference of squares? Notice the journey we just went on. The journey we just went on was taking our equation to a new equation where we can actually use the zero product rule. I now have something times something equals 0. So now we can set both of those equal to 0. And we would say x minus 8 is equal to 0, and x plus 8 is equal to 0, which means what? Yeah, x equals 8 or x equals negative 8. We just finished step 3, solving for x. We just solved for x. Mathematically, what that means is if I plug either of those numbers into this equation, what should happen? It'll be true. Yeah, it'll be equal to 60. Okay. Well, there's still one last thing we have to do, and that is verify truth. That is, verify truth within the context of the actual original problem. Remember, the original problem didn't say solve for x. The original problem said find the length and the width of this rectangle. So let's take both of those answers and take a look. If I let x equal 8, I'm going to go back here to my rectangle. Then my two sides are 8 plus 2, which is 10, and 8 minus 2, which is 6. What's the area of that rectangle? 60. 6 times 10 is 60. Okay, well, great. X equals 8 is definitely a solution. X equals 8 is the solution for x, but the answer to the problem is this right here, this nice little diagram. Okay, what about negative 8? What about negative 8? What do I get if I plug in negative 8? What's negative 8 plus 2? Negative 8 plus 2?
Oh, negative.
Negative 6. And what's negative 8 minus 2? Negative 10. Now, take a look at this diagram and tell me all the things that don't make sense about it. Yeah, there's no such thing as negative sides. And furthermore, just look at the relative sides. Like they're saying that the negative 6 is the longer side and the negative 10 is the shorter side. Like everything about this is nonsense, right? This is nonsense. And yet, what's the area? 60. Doggone it. So mathematically, it's true. Mathematically, it's true that the area turned out to be 60. But realistically, this solution is nonsense because you can't have two sides being negative 10 and negative 6. So here's what we say. X equals 8 is the solution for x, whereas x equals negative 8 is a special word called extraneous. You would label that solution extraneous. In fact, you would even go back to your original where you found x equals negative 8, and you'd cross it out and write extraneous. The definition of the word extraneous is true, but nonsense. It's true, but it's nonsense, right? -8 is true. It makes the equation true, but it's nonsense in terms of the problem. So what's our final answer?
Like, and
6 by 10. Right? Because the original problem said find the length and width of the rectangle. I suppose technically I should say 10 by 6. Find the length and width, 10 by 6. That's our answer. And you could circle it. You could smiley face it. That would be the end. And that is the end of the problem we verified truth. So these are the 4 steps that we're going to use over and over in this class as we guide ourselves through challenging word problems that we need to solve. We draw a picture, we build an equation, we solve for x, and then we verify truth. Because not every solution that we get from the algebra is actually going to be a solution to the word problem. All right? All right, wonderful, folks. Now, number 62 is very similar. And I think for the sake of time, I'm going to leave that one for you to do for homework. And right now, we'll go ahead and take our break. It's 9:09. Everybody be back in the room at 9:19. And we'll keep going. Thank you, folks. Okay, great. What's your question? Right, like if you get down to 8 and -8, well, first of all, if you just left it there, that would because you didn't answer the question. Like, and yeah, you need to put both of those in to show which one is actually the real answer. You say this one's the real answer,
I don't.
and this one is the extraneous.
I have an extra
So yeah, I
pencil.
want to say the word extraneous because that lets me know that you guys are your entire problem, and you go all the way to the end to know for sure what the answer is. Yeah. Oh my gosh, I need to collect that. Thank you.
Right there's next to it. So it's like this bridge to walk along the street and you take those. And it's explained for I'll do it for you.
Folks, I completely forgot to ask for your midway quiz. And so if you're in the room, if you want to go ahead and bring it up, you can bring up your midway quiz and we'll make a stack. Silly me.
Are you getting like the videos to start today?
What's that?
Or
Was I going to give that to you today? No, I'll give it to you next time. Thank you.
So if it's negative, it's automatic.
Yeah.
I'm actually did like this. Yeah. No, I didn't do all of it, just like the ones that.
Yeah.
Was 6.6 the same as 6.5? Was it just combined?
Hmm?
6.6 combined with 6.5?
Oh, is it not listed in there? I might have just accidentally not put the subtitle.
Okay.
So it's in there somewhere. I just didn't mark it off. Good question.
Not really. Right now, around 62. Chance it rains.
Did you make this? Hey there. Oh, yes, thank you. I'll take it.
First, I had to get my second one, or like previous first one. I'll let you know.
Thank you, sir.
Yeah, he was taking.
Thank you. Folks, if you haven't done so already, will you please bring up your midway quiz? I forgot to ask for it at the beginning of the hour.
Yeah.
Think what? Think Andrew? Think April? Think Andrew? All right. Hey, thank you. Come on back, folks. All right, let's continue. We are about to do a really fun problem. I don't know what that makes you think when I say it's a fun problem. I don't know if that makes you think, oh, good, a fun problem, or you think, oh, if Mr. D thinks it's fun, it might not be fun. But no, truly, it is going to be fun. This is an exceptionally great problem. It is a great problem. So I'd like us to start, we're all looking at number 63. I'd like us to start, well, everyone read the problem yourself and draw a picture that you feel captures the information from the problem. So that's what I'd like us to do. I'd like everyone to take 2 minutes and on your own, draw your own picture that you believe captures the information being presented in the problem. Try to have your picture include all of the details that you see in the problem statement. And we'll just take a couple minutes for each of you to draw your own picture and for you to get down all of your labels. There we go. Okay, great. Okay.
Thank you.
How do you like it? This phone?
Wait,
Do you like it?
yeah,
Let you go.
it's the size.
How do you turn it off?
You just tap it.
So,
All right, folks, let's compare. I just walked around the room, I just looked at all of your drawings, and I just grabbed a snapshot of the different types of drawings that I saw. So first of all, this is wonderful. this is a wide variety, right? This isn't just one drawing that you all came up with. There were a lot of different ways that you interpreted it. So let's look at each interpretation. The first one is basically just a rectangle. You know, you've got the rectangle there, and then from there you're going to build on your problem. This one, what do you suppose this person was drawing?
Hi.
Yeah, the gravel, right? Like gravel is just kind of like this messy thing, and so they had the gravel path going around it. I thought that was fun. What was going on in this one?
The same.
Yeah, the same, but this time the gravel path was this fun thing that kind of went all the way out and around. It didn't even touch the garden. It was just kind of a gravel path that went around outside of the garden. That was an interesting interpretation. And then here, someone kind of actually drew in lines as if to represent like it was a sidewalk or something, and you had the break in the concrete. And then finally we had this drawing where you had an inner rectangle and an outer rectangle. So all those possibilities in your minds now, let's read the problem again together. A rectangular garden, stop. Do you all have a rectangle on your page? Good, that's a really good start. A rectangular garden has dimensions of 20 by 13. So we could probably begin by making sure that the inner rectangle, whatever rectangle you drew on the inside, should have the measurements 20 by 13, right? And the longer side should be 20 and the shorter side should be 13. And in fact, let's just go beyond that real quick. What else could we go ahead and say about this rectangle whose dimensions are 20 by 13? The area would be 260. Because that's length times width, 20 times 13 is 260. So far we've captured the information from the beginning of the problem, which is a rectangular garden has dimensions of 20 by 13. And by the way, a couple of you even drew in some really nice flowers. That's fun. So you had some flowers going on in there. Okay, so we have our garden, it's 20 by 13. Great drawing. Next, a gravel path of equal width is to be built around the garden. So how do we draw that? How do we draw a gravel path of equal width going around the garden? This is a fun drawing because it has shading and it shows the gravelly nature of the gravel. Although, what would we want to do to this just to make sure it's equal width all the way around the outside? Maybe give it some sort of boundaries, right? That way we just know that it's equal going all the way around. Now this one was fun and maybe like a little Picasso-y. Is it possible for us to measure the area of a curvy gravel path?
No.
If it's curvy, I don't think we have any mathematics to actually measure the area of something that's not a rectangle. So this one might not work out so much if it's all curvy. Should we make the gravel path attached to the garden or not attached? Probably attached. You know, I think this is probably more fun, you know, as far as, you know, feng shui. But in terms of actually calculating this problem, we probably need the path to be attached. And then this one was also fun because it kind of showed the sidewalk nature of it, but all those lines might just distract us from what's happening. So, folks, I think what I'd like to ask us to do, no matter what your drawing looked like, let's all now come together and draw the same picture so that we're all starting out with the same idea. Now, all of your drawings were fantastic. It was a really good brainstorming session. So, if you don't mind, start a new drawing with me, and we're going to show the garden, which we knew was 13 by 20 and therefore had an area of 260. And we're now going to draw the gravel path of equal width going around the outside. So you'll just go ahead and draw an outer rectangle going around the outside. So we have an inner rectangle and an outer rectangle. And how wide is our gravel path? How wide is it? Was it?
We don't know yet.
Yeah, we don't know yet, and therefore we call it X. So here's what you want to do. You want to use little arrows to suggest, like, so how wide is that right there? That's X. How wide is that right there? That's X. How wide is this right here? That's X. How wide is this right here? That's X. We want to have some little indicators going around outside that really let us know how wide that strip is going around that whole path. Okay, how does our picture look so far? Have we captured all of the information from the problem? Let's try reading it again. A rectangular garden, done. Has dimensions 20 by 13, done. A gravel path of equal width, done. Is built around the garden. How wide can the path be if there's enough gravel for 234 square feet? Now, what does that mean? Where do we put the information about the gravel? There's enough gravel for 234 square feet. Yeah, the outside part, the gravel itself. The area of this is 234 square feet. Okay, the inner rectangle has an area of 260 square feet, but the outer area has an area of 234 square feet. So let's just write that in. A equals 234. So I now have the area of the inside rectangle, that's 260. And I also have the area of the outside border, and that's 234. Now, admittedly, I suppose this drawing could look a little different, but have we captured all the information from the problem?
Yeah.
Are we really sure?
Well, we haven't done that.
Don't we?
Well, that's true. We haven't done the problem yet. We don't know how wide it is yet. That's true. But did we capture all the givens? What were we going to say, Junior?
So the gravel path has the equal width of.
The gravel path has an equal width of x going all the way around outside. Yeah, so it's always x units wide. Okay, well, I think we captured all the information. We now have a really good floor plan of what we're looking at. So what's the question? How wide can the path be, right? Now, just to be silly, right, we could, if we had a garden, I could put a gravel path that's only 1 inch wide, right? Would I have gravel left over?
Yeah.
I probably have a lot of gravel left over. Like I went to Home Depot, I bought all this gravel, I put it in my truck, I brought it all the way home. Do I just want to put a little 1 inch strip of gravel around the outside? Probably not, because then I have this huge pile of gravel left over. But could I make my gravel path 10 feet wide?
No.
Did I bring home enough gravel for that? I didn't bring home enough gravel for that, right? I could probably start putting in the gravel, and then I would probably get that far, and I'd be like, oh darn, I ran out of gravel. And then I wouldn't have enough to go all the way around the side. So you can see the question we're asking is, how thick of a strip can I make with the gravel that I have? I don't want to have gravel left over, and I don't want to run out of gravel. So how wide will that strip be? That's our question. Anyone want to just take a guess how wide it's going to be? I mean, we really have no basis for guessing right now, do we? I mean, you could say 5 feet, you could say 10 feet, you could say 1 foot. Yeah, Ellen?
Divide 234 by 4
Could you divide 234 by 4?
to see like the sides.
Well, I don't know. Can you? I mean, you could try. I don't think it's divisible by 4. And plus, we're not talking about perimeter. Why would you want to divide it by 4?
I don't know, I was thinking maybe you can find like the whatever in the 4 parts of.
Oh, okay. Now that's an interesting idea. Elna is saying maybe find out how much area goes here and how much area goes here and then how much area goes here and how much area goes here. Okay, now that's an interesting thought. You could try to chunk it up, right? Okay. Well, everybody, we're done with step 1. We drew a really nice picture. Now let's build an equation. What equation do we have to use right now?
The equals 0.
Well, we want to eventually get to something equals 0. But what's the concept we're talking about?
Area.
Area. Right, so everybody go ahead and jot down. The formula is area equals length times width. But as I did before, let's write it down backwards. Length times width equals area. Well, what are we going to find the area of? It's true that our only concept that we have to play with here is area. So can we do the area of the inner rectangle? Sure, we actually already did. That would be 13 times 20 equals 260. So if I find the area of the inner rectangle, did that help me solve for x? No, we still don't know what x is. So what other rectangle could we find the area of?
Yeah, that's good.
Yeah, the bigger rectangle, right? To find the area, we have an inner rectangle. That was our inner rectangle, right? That was the inner area rectangle. What about the outer rectangle? Could we find the area of the outer rectangle? I mean, we can, theoretically, it's a rectangle, right? So it's a rectangle, we can find the width and the length.
You just add the areas?
Well, that's a good point. We could just add the areas, right? What's the total area of the whole thing?
494.
494? That's certainly true. So the area of the whole thing is 494. That's true. The area of the whole thing is 494. But what's the length and what's the width of the whole thing? So let's start with the width, or the length, I guess. This is the length. How wide is the whole thing? You know that it's at least 20, but it's bigger than 20. How much bigger than 20 is it? You've got an extra width over here, and you've got an extra width over here.
2x.
Yeah, there's 2 x's there, right? You've got the 20, the x over here, and the x over here. So technically, the total width, the total length is x plus 20 plus x, right? If I just read them in order, that was a width of x, that was a width of 20, and that was another width of x. So I've got x plus 20 plus x, which simplifies to 2x plus 20. Right, so that's our total length of this garden. Do you agree?
Yeah.
Okay, so if that's our total length, what's the total width of our garden? Yeah, 2x plus 13, following the same reasoning. We've got this length is 13, and then we've got a little x right there and a little x right here, so we've got x plus 13 plus x. So the total height of this garden right here is x plus 13 plus x, and you can combine like terms again, and you get 2x plus 13. So plugging this now into the area of the outer rectangle, our total length is 2x plus 20, and our total width is 2x plus 13. And we just added the total area by adding the inner area plus the outer area, 260 plus 234. So what's our formula? 2x plus 20 times 2x plus 13 equals 496?
494.
Hey,
494, thank you. There we go. Is that the right equation for the total area of the whole thing? I think so. I think so, unless I made a mistake, like writing 6 instead of 4. Okay, so did we do it? I'm going to erase my check mark so I have the satisfaction of doing it again. Did we draw a good picture? Yes. Did we build an equation? Yes. Now what do we get to do? Yeah, now actually just solve it. Notice how much work we had to do first. That was a lot of work you had to do before you just start whacking away solving for x. Right? That's a lot of pre-work. Okay, so now, folks, let's do it. In order to solve an equation, what do we ultimately need? Equal to 0. We need equal to 0. So we know we need to bring the 494 over here to the left. And what do we have to do with this? We have to FOIL it and distribute it so that we can get just a basic trinomial equal to 0. We need a basic trinomial equal to 0 so we can turn that addition problem into a multiplication problem and set each binomial equal to 0. So let's do it, folks. Let's start by FOILing. So to FOIL, first 2x times 2x is 4x squared. Outer, 2x times 13 is 26x. Inner, 20x times 2x is 40x. And last, 20 times 13 is 260. And all of that equals 494. What do we do next?
You can combine the two.
Yeah, we can combine those like terms in the middle there. So now we have 4x squared plus 66x.
Yeah.
Now, I mean, we can make it in 2 steps, but I do want to go ahead and bring that 494 over. I hate to combine too many steps together. I'm just going to write my 260 equals 494, and then I'll go ahead and subtract my 494 over. Then what do we get? 4x squared plus 66x minus 234. Equals? 0. Okay. If you were to think about breaking this down into phases, we drew our picture, we built our equation. The first phase of this equation work was to turn it into standard form. And standard form is just like the first step. You need the whole thing to equal 0 so that you can now convert this addition problem into a multiplication problem. So phase 1, we just converted it to standard form. Now what do we do?
You subtract the 230. No.
Well, we want to keep the 234 over here because we want the whole thing equal to 0 so we can eventually use the 0 product rule.
Pull a 2 out.
Yeah, we can take out a 2. Can we take out more than a 2? No, because 66 divided by 2 is 33. That's odd. So we're probably stuck taking out a 2. Let's take out a 2. So now we have 2x squared plus 33x minus 117.
Yeah.
Now we've got that little pesky 2 out front. What can we do with it?
Get rid of it. Sorry.
Yeah, we could just get rid of it, right? We could divide the 2 off and just get rid of it completely. It's no longer part of the problem. We don't have to keep looking at it. So now we have 2x squared plus 33x minus 117 equals 0. Now are we ready to factor? Yeah, we're ready to genuinely factor now. So now we can actually factor this thing. Can we just say what multiplies to equal 117 that adds to make 33?
No.
No, because there's a 2 up front. So we get to do the longer factoring technique. And because I'm almost out of room right there, I'm going to bring this up here so that I can continue working with all of you. And let's see, I'm going to rewrite that too so that it's a little out of the way. There we go. So continuing on our merry way, 2x squared plus 33x minus 117 equals 0. So we're going to factor 2 times 117. What is that?
It's 234.
Negative 234. And so what multiplies to make 234? Well, 1 and 234, 2 and 117, 3 and something. Anyone have a calculator?
78.
3 and 78?
Mhm.
Okay, great. 4 and nothing, 5 and nothing, 6
34.
and 34, super. 7,
No.
8,
No.
No.
9.
39, 6 and 39.
26. 9 and 26.
9 and 26 works? Really? 9 and 26 works?
No,
Yeah.
no.
Yeah.
It was
No.
234.
Are we doing 234?
Yeah.
I don't think even that 6 worked.
No, it's 6 and 39.
6 and 39, there we go.
9 and 26.
All right, so clearly we have to be careful, right? We want to have our calculator out dividing these numbers. So it was 2, it was a 3, it was a 6. Oh, yeah, now 9 would go into it for sure. So then we could take out another, what, was it 9 and 26 someone said?
Yeah.
Okay, yeah, that was correct.
What was wrong before?
We had 6 and 34. Or maybe I just heard someone wrong and I wrote down the wrong thing. Okay, are we done with the factor table?
Yes.
Oh, I think there's one more, 13 and 8. Okay, so that was just its own little fun and excitement right there, right? Coming up with a factor table for this totally random number, 234. We need the difference to be 33. Where is our difference, 33?
Would it be negative 6 and 39?
Yeah, 6 and 39. And we do need it to add up to a positive 33, so that'll be a positive 39 and a negative 6?
Yeah.
All right. Okay, so continuing on our way, we're going to rewrite the positive 33x. We're going to rewrite it as negative 6x plus 39x. So we'll write down 2x squared minus 6x plus 39x minus 117 equals 0. And then we factor by grouping. What comes out of 2x squared minus 6x?
2x.
Yeah, just a 2x. That leaves us with an x minus 3. And then what comes out of 39 and 117? Now, right now, if you don't know what goes out of 39 and 17, what would you try first? Be optimistic and try 39. Right? You want to be optimistic. You know, go for it. Just try dividing the bigger number by the smaller number. That's sheer optimism. Who knows? Maybe it'll work. So on your calculator, can you divide 117 by 39?
Yes.
Oh, goody gumdrops, right? So that's your first shot, is to be optimistic. So 39 did come out, and that leaves us with x minus 3. And that's a good thing. We got x minus 3 twice, so we know we're doing it right. We can keep going. X minus 3 and 2x plus 39. Folks, we've come a long way. We started out, remember, with a product equaling 494. And we just did a whole bunch of algebraic manipulation to get a product to equal 0. Just imagine, okay, philosophically, that's what we just accomplished. That was a long journey. We started with this product equaling 494, but that wasn't the zero product rule. That wasn't going to help us. So we had to manipulate, FOIL, move things left, factor, and now we created a new product that equals 0. Now we can actually use the zero product rule. That was epic, what we just did. All right, so this times this equals 0, therefore, either x minus 3 equals 0 or 2x plus 39 equals 0. And so our solution is either x equals a 3-foot path. What do you think? Does that sound reasonable? 3-foot path?
Yep.
That sounds reasonable for people and humans and people who like to walk. 3-foot path is pretty good. And then 2x plus 39, that'd be 2x equals negative 39. And so x equals negative 39 halves, which is negative 19.5. How does that sound? A gravel path that is negative 19.5 feet wide?
It's too big.
I mean, 19.5 is a pretty wide path anyway. That's like this wide. So right, you've got a gravel path going around your garden That's the width of this classroom. That's a little weird. But also, the length is negative. You can't even have a negative path. So which one of those answers is correct?
X equals 3.
Yeah, x equals 3 is the correct answer. What do we call x equals negative 19.5?
Extraneous.
Extraneous. That solution is extraneous. True, but nonsense. It is true that if I plugged in negative 19.5 into my original equation, that would equal 494. It would. But it makes no sense that our garden would have a path that's negative 19 and a half feet wide. Especially because, folks, 19 and a half feet, how wide is the whole garden? 20 feet. Could you imagine making a path around your garden that's just as wide as the garden was? That would be weird. There's no feng shui there. You wouldn't be hired back to build another garden. All right, so the gravel path is 3. Is that what the question asked us to find?
No.
How wide can the path be? Yeah, that actually was what the problem asked us to find. 3. Now, because we are professionals, we are all professionals, how will we present our final answer? As a diagram. And so the width of the original diagram is 20 by 13. The width of the gravel path is 3. And so what's the actual dimensions of the outside?
26.
Yeah, 20 plus 3 plus 3 is 26. And then 13 plus 3 plus 3?
19.
19. Now, here's our last way to check this. Is 19 times 26 equal to the total outer area that we set? Is 19 times 26 actually equal to 494, the total area we said it would be?
Yeah.
Yeah, if you type it in your calculator, it is. Now, right then, this is the moment of truth for us. Like, we nailed it. We definitely came up with the right number 3 that made our equation true. Because remember, this was our equation that we had to make true. And the way to make this equation true is by plugging a 3 into it and seeing if it equals 494, which means putting our 3 in the diagram and checking to see, was the outer area really 19 by 26 equal to 494?
Where did you plug 3 again?
Into this expression, 2x plus, 2x plus 13. So because that gave you this width was 13 plus another 3 plus another 3. So that's 3 plus 13 plus 3. Or in other words, 2 times 3 is 6 plus 13 is 19. And then over here, 2 times 3 is 6 plus 20 is 26. Folks, that was an epic problem, right? Would you say that?
Yeah.
That this was an epic problem? I think it's an epic problem. In my previous class, someone said this problem inspires dread. Like, whoa, this was a big problem. And you know what? It was. That was a really big, long problem. And the good news is, I have another one for us to do so we can practice. Now, obviously, we don't have time to do this right now. But when should you do it? When should you do it? Right now. You should go home and have a snack, take a nap, whatever you want to do. But today, do number 64. I want you to try it out. Try number 64 today while it's still fresh in your mind. Because the setup is the same. Okay, the setup is exactly the same. All right, folks, really nice work. If anyone has any questions, please come ask me. Did I get everyone's quiz? Did I get everyone's quiz? Everyone handed me their quiz?
Not enough paper in the world, Mr. G.
For that problem? You know what I mean?
Yeah.
Yeah. Guys, we need a little more room.